when we talk about sequences, sequences is really literally just a list of terms. And so if we take a look at some examples, so we're talking really about just a list of terms. And in that respect, I think this is a kind of a really good summary of what we're getting at. We say, first of all, a sequent is a function. Apparently it's so important I say it twice. It is a function, and I'll get into why and how we can look at it that way in just a minute. But this goes on to say whose domain is the set of positive integers. So if we think about the domain, we're talking about the set of x values from a function standpoint. And so from a sequence standpoint, we're talking about the set of values for n. And n is known as that term number. And so if you think about it, that term number starts with term 1, then you go to term 2, then you go to term 3, and et cetera, et cetera. So in other words, the first 6 terms here, when n equals 1, then a sub 1 is 3 plus negative 1 to the first power, which is 2. And when n equals 2, a sub 2 is 3 plus negative 1 squared, which is 4. And then if we look at the third term of the sequence, when n equals 3, we can start to see a pattern take place in this sequence. So negative 1 to the third power, so we're back at a value of 2. And so on and so forth. So if we just kind of complete this, this problem here, we can see that there is a distinct pattern in these terms here for the 5th and the 6th term. Probably can fill them in without doing a whole lot of math here. This one's got to be 2, this one's got to be 4. And so when we're talking about this, here is that domain. It's the set of positive integers. So there's your domain. Here is your range, the set of y values. And so if we look at this from a function standpoint, we can look at this as 2, 4, 2, 4, 2, 4. And we can look at this graphically. If we want to talk about it graphically, we can look at this as 1, 2, 3, 4, 5, 6. As we graph this, when for the a sub 1 term, we're up here at at 2, and then the next term we're at 4, and the next term we're back at 2, then up at 4, then back at 2, and up at 4. So if we look at like a vertical line test, it passes the vertical line test. For every input, there's exactly one output, so it passes all of those characteristics that we refer to as a function. And so we can really write this as, for instance, y equals 3 plus negative 1 to the x power. We can really write that in function notation. So, so that's kind of what that statement is getting at. And the nice thing is then, as we talk about sequences, we can talk about the limits of sequences just by talking about the limits of function. They're going to follow those same principles. If we take a look at this next example here, it says write the expression for the nth term of the sequence. What we're looking at here is this nth term of the sequence. Really, that's what we would call a pattern. And if we were doing this in algebra or something, look for the pattern. So when we talk about looking for patterns, we're talking about, you know, looking for patterns with these for mathematical functions, maybe adding in these functions as well as we get into more complicated patterns. But as we can see, as we go from 3 to 7, if we just start out with the basic 4 operators here, we can add 4 to get to 7, and then we can check to see if that works for 11, and it does, and if it works for 15, which it does. So we know we are just adding 4 here, and so we can then come up with an expression for this sequence. Now add 4 kind of has this recursive quality to it. In other words, if I'm just going to add 4, then I need to know the term prior to it, so I can add 4 to it to get the next term. And that's a recursive behavior. When we want an expression for the nth term, we have to write that expression with respect to the first term. So, for instance, if we look at the first term to write this a sub n term, we really need an a sub 1 term, and then plus some sort of expression that is going to allow us to add 4 multiple times. So if we look at this, to get a sub 1, we took 3 and we added 4 0 times. If we look at the second term, which is 7, we started with 3 and then we added 4 1 time. And if we look at the next term, the third term is 11. We started with 3 and we added 4 2 times. And if we look at the fourth term, that's 15. We started with 3 and we added 4 3 times. So if we see that, then we can start to tie a pattern back to this sequence number. Okay, the fourth term has 3 multiples of the 4. This term has 2 multiples. This term has 1 multiple. So if this is our term, then this is related to that term number by being 1 less. So if we want our nth term in the sequence, which would be a sub n, we can take 3 and we can come up with a symbol for add, and we're going to add 4 1 less time than we are out in our sequence. So here is our expression for the nth term. Now if you notice, we could also simplify that expression. We could do a little math here and distribute, and we could then combine terms, and so we could also have this mathematically equivalent term for the nth term of the sequence. Both correct, just mathematically equivalent. The advantage here is this is not recursive. This is always going back to the beginning term, and so from this point we can determine any term of the sequence. If we want the 100th and 127th term way out there, then we know that we can just start with 3 and we can add 4 127 minus 1, or 126 times. And so we don't have to have the first 126 terms in order to get this term. We can just get it right off the bat from doing the calculations. So that would be 3 plus, let's see, 127 times 4. Here are the 2, that's 10. 4, that's 508. And so the 127th term is 511. So when we're looking at finding the limit of a sequence, we can really take a look at this as really finding a limit of a function. And we can use all those things we've used in the past to find limits of functions L'Hopital's is going to be a really common go-to method to find a limit of an expression. But all the other ones too, rewriting, canceling, dividing by highest powers, all of those things are going to become, we're going to come in handy here. And so if we take a look at the limit of a sequence, it says here, let a function be a real variable such that the limit of the function equals the limit. And we're going to use that information that we can take a look at a sequence as if it were just a function for every positive integer. Then the limit of that sequence really just becomes the limit of that function directly. And so we're really talking about the limit of a function being one and the same as the limit of that sequence. And then properties of sequences are really just properties of functions. If we've got two sequences, A and B, and just like if we have two functions A and B, if we add or subtract them, we can just add or subtract their limits. If we multiply them, we can just multiply their limits. If we multiply a function by a constant, we just multiply the limit by the constant. If we take a ratio, we can take a ratio of the limits. So all of those properties are the same properties as what we have for functions. If we take a look at this example here we have a similar sequence that we had on the previous page. It says determine the convergence or divergence of the sequence. And so when we're talking about finding limits, we have to talk about that determination of a limit. And when we take a look at a couple of ways we can do that. We can do that algebraically, like I mentioned at the top of this page, or we can take a look at their individual terms and see if those terms trend towards a specific value. And so if we look at the first term here, that's 1 plus negative 1 to the first power, which is 0. If we look at the second term, it's 1 plus negative 1 squared, which is 2. This one ends up being 0. A sub 4 ends up being 2. A sub 5 ends up being 0, and so on and so forth. And so we have this oscillation between two values. And so since we have this oscillation between two values, this does not have a limit. So if we take a look at the limit, and I'll write this in function notation, as x goes to infinity, it would look like 1 plus negative 1 to the x power. And negative 1 to the infinite power is an indeterminate form. So we'd use L'Hopital's here to come up with the fact that the limit does not exist. If we take a look at this next example, we have to do a little review as to what this explanation point means, and that's that factorial notation. And so when we talk about factorials, we're talking about, taking a number and multiplying it by subsequent smaller numbers all the way down to 1. So the 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. And so when we talk about working with factorials and fractions, 7 factorial over 5 factorial ends up being 7 times 6 times 5 times 4 times 3 times 2 times 1. 5 factorial ends up being 5 times 4 times 3 times 2 times 1. And then we end up with that nice phenomenon of canceling. And so we're just left with 7 factorial. Sometimes people will write this as 7 times 6 times 5 factorial. And we'll just stop reducing the numbers until they match the factorial that's in the other portion of the fraction. And so this ends up being 42. And so we have to deal with this in that same fashion to get it to simplify. And the important reason to get it to simplify is to get rid of those factorial expressions so we can actually determine the limit. And so we're going to work with rewriting this. So n minus 2 factorial, that's the smaller one. N is the bigger one. So if we think about n factorial, that's going to be n times 1 littler than n, which is n minus 1, times 1 littler than n, which is n minus 2, times 1 littler than that, which is n minus 3, times 1 littler than that, which is n minus 4, and so on, all the way down to times 1. And so if we look at this, then n factorial is bigger than n minus 2 factorial, since this is, you know, the value n and with 2 taken away. And so we're going to leave the smaller value unchanged, and we're going to rewrite the bigger value like this. And so we're going to kind of use the approach then of that we used over here, where I can write the bigger factorial as 7 times 6 times really 5 factorial. As soon as I match the number in the other location of the fraction, I'm going to just stop and put a factorial on it. So I have n times n minus 1 times n minus 2, and I know it's times n minus 3 and minus 4 and minus 5 and minus 6, but that's all just n minus 2 factorial. So I'm going to rewrite the larger factorial like this, and then I can see that these are going to cancel term from term all the way out. And so an equivalence, you know, we talked in the previous page about equivalent expressions for nth terms. Here's an equivalent expression. It's 1 over n times n minus 1. And so these two are mathematically equivalent, and this is much easier to find the limit of. So when we look at finding the limit of this, we can write it in function notation if we want to. You don't have to. But this would be looking at the function 1 over x times quantity x minus 1. And so if we take a look at the limit here, and I'll take a look at the limit of the function as x goes to infinity. In other words, if x is going to go to infinity, then this value is going to go to infinity, which means the n's are going to infinity. So when we take a look at this limit here, we're looking out at the nth term, or the infinite term. And that's determinant. We can put infinity in the denominator here and get 0. So the value here, the limit is 0. So that means that the limit then, as we write out infinitely many terms for this sequence, equals 0. So the terms end up going to the value 0, which means graphically speaking, if we would look at this with a graphing calculator, oops, so if we would get out the graphing calculator here, there we go, and we look at this as a function. So I'm going to go ahead and put that in y1, 1 divided by the quantity x times the quantity x minus 1. And we look at that graph. There's the graph here for those terms, and if we give a window here that is maybe -1, and how about let's go out to 50. That's pretty many terms, and this is -1. Then we can see that this goes to 0 really fast. So the value of that function really goes to 0 pretty darn fast. So if we just capture that and paste that here, then we can see that this, if I can follow that along really quickly, here is the function for the positive domain. I'm kind of exaggerating it, but we see that it goes to this 0 line really fast. So we know that the limit then of that sequence is 0. And likewise, its mathematically equivalent expression, n minus 2 factorial over n factorial, also goes to 0. And so if that being the case, then we call this convergent, because it converges to a finite value. So the values of the terms converge to a finite value, and that value is 0. So in recognizing an expression for the nth term, it's really all about recognizing patterns, and and sometimes there are many equivalent expressions for the same nth term. So trial and error kind of factors into it. Really, I guess instead of trial and error, maybe a better expression is an educated guess. In other words, know things like know patterns of squares and square roots. Know that 2n is always even. Know that a 2n plus 1 or a 2n minus 1 is always odd. So, if we can kind of make an educated guess, it'll help us. In looking at this, just to kind of practice this, I see a fraction for every term except for the first term. So the first thing I'm going to do is make sure they all have the same pattern. And so I'm going to write that first term as a fraction, 1 over 1 equals 1. Now I can look for patterns. I see that my top is always the value 1. And that's not changing, so it's a constant in the nth term expression as well. And then my first term has a 1, my second term has a 2, my third term has a 4, my fourth term has an 8. Okay, so we're not just doubling our term. We're doing something else. With this expression, and so we have to kind of look at this going, well, they're all even, and it looks like if I take this multiply by 2, I get this one. And if I do that recursive thing again, and a recursive behavior is an indication of something, and I'll get to that in a second. But if we look at this recursive nature is always times 2. And if we get a recursive nature in that, if we can see that recursive behavior is always successive multiples. So in other words, since this is always times 2, we're going to have 2 to a power in the denominator. If this was 1, 3, 9, 27, 81, where it was always times 3, then we'd have 3 to a power in the denominator. So that recursive behavior helps out to find out how to write the denominator. So we know we have 2 to a power, and for the first term, the a sub 1 term, the power needs to be 0. 2 to the 0 is 1. For the a sub 2 term, the power needs to be 1. For the a sub 3 term, a sub 3 term is a 4. The power should be a 2. So you can see a pattern between the term number and the power needed. The power needed is always 1 less. So the power must be n minus 1. So that's kind of some advice as to how to find patterns to get that expression for the nth term. If we would take it's not asking for this, but if we take the limit, I'll write it in sequence notation now as n goes to infinity. Of this sequence to the n minus 1, we get 1 over infinity. 2 to the infinity is infinity, and so this also goes to 0. So the infinite term is 0. So this has a limit of 0. When we talk about a limit, for instance, like sine of n over n, if we look at that sequence, when we're dealing with trig functions, we have this, I almost want to call it cyclic behavior, where where the value fluctuates between -1 and 1, almost like the patterns from the previous page, where we had the sequence bouncing from 0 to 0 to 2 to 0 to 2 to 0 to 2. This also has that cyclic behavior. And so it kind of bounces back and forth. And so if we get the calculator out again, and we just graph this, since we can really look at the function notation. If we graph the sine of n over n, and we want to be sure when we're doing this, we understand that these trig functions are in radian mode, so we want to be careful about keeping them in radian mode. And I'm not quite sure how I did that, but let's get rid of that and get the calculator back up here, so keep them in radian mode. So we're going to type in sine of x over x. And if we look at that graph, and so we're going to need to adjust our window to accommodate for trig values. Let's start at an x min of 0. We don't need negative values for our domain. Let's go out to, let's say, 10 pi. So we're in radian mode. There we go. We'll keep our y min and max at 10 and minus 10, just to see what this looks like. So if we see that, tough to see. So let's go ahead and zoom in. So let's go ahead and set this window at -1 and 1. Just to zoom in a little bit, we see that this function oscillates, just like those earlier functions, but it kind of oscillates, but then it dies out. We call that damping, and so that behavior, that damping behavior, is indicative of going to a specific value, and so we have to kind of look at this from a symmetrical standpoint. It's oscillating above and below some sort of center point, and that center line is the value 0. So graphically, we can see it. The sequence goes to 0 as n goes to infinity. How we show that algebraically is we pick something smaller than sine of n over n. And so when we want to pick something smaller than this, we look at this lower bound of what the sign could be, and we know the minimum value is -1. So we're going to look at the function -1 over n, and then we're going to look at what the sign could be at its biggest, which is a +1. And so we're going to look at the function of 1 over n. And if we do that, so we will graph, we're going to go ahead and graph -1 over x, and let's make this, there we go, let's make that a kind of a thicker line, and we'll make this a thicker line as well, and then we're going to graph 1 over x, 1 divided by x. So as we graph those, we can see there's our -1 over x, there's our +1 over x, and we can see that those two functions kind of trap, so to speak. Those two functions, so this is my 1 over n, this is my negative 1 over n, and that those two things trap sine of n over n. And so since they trap it, then if we can determine the limit of 1 over n and the limit of negative 1 over n, then if those are going to the same point, then anything in between it has to be going to the same point. So if we take the limit as n goes to infinity of negative 1 over n, again, that's determinant, that's negative 1 over infinity, which is 0. And if we take a look at the limit here as n goes to infinity of 1 over n, that's also determinant, that's just 1 over infinity, that is also 0. So since that is, and this is why we call it the squeeze theorem, since that is squeezed in between those two other functions, the limit here as n goes to infinity must also go to 0. And so we call it the squeeze theorem for, I think, obvious reasons here. Is that we just keep squeezing the sine of n over n in between these other two functions that we know the limits of. So the squeeze theorem allows us to talk about this idea of monotonic. And the idea of monotonic is that we have something of a sequence that starts at a value and then gets either subsequently bigger or subsequently smaller. So if we take a look at sine of n over n, and we take a look at that, it gets smaller, then it gets bigger, then it gets smaller, then it gets bigger, then it gets smaller, then it gets bigger, then it gets smaller. In other words, this function turns around several times, many times. And so that is not monotonic. So sine of n over n is not monotonic. It turns around many times. But however, 1 over n is monotonic. It starts with a big value, and its values get smaller and smaller and smaller and smaller and smaller. Okay, and that's what, so if the values are getting smaller and smaller and smaller and smaller and smaller, they are not increasing. So 1 over n is what we call non-increasing. Non-increasing means it either gets smaller or it stays the same value. Okay, it does anything but increase. And likewise, negative 1 over n starts really small, or what I would call big negatives. And then it gets bigger, 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 bigger as it goes towards 0, and 0 is the biggest value that it gets. So 1 over n, or negative 1 over n, is what we call non-decreasing. In other words, it gets bigger or stays the same. It never gets smaller. Okay, so when we have these functions that, what I would say, don't turn around, they just start at a big value, get smaller, or start at a small value and get bigger, those are called monotonic. So this is an example of monotonic non-decreasing, monotonic non-increasing. Okay, so we can talk about that then in terms, in a couple of ways. Either we can talk about it algebraically, or we can talk about it involving calculus. So let's kind of take a look at each one of those ways. So if we kind of put we'll save this example for a little bit later here. If we take a look at the sequence 1 over n, then if we write out a few terms, we can see that it is always getting smaller, so it's non-increasing. Okay, and so we can look at that algebraically. by looking at the terms and seeing how the terms trend, or we can look at it using calculus by saying, if here is the graph of 1 over n, then the derivative of that graph, anywhere we take, is going to be, the derivative of that graph is going to be less than 0. It's going to be negative. And so, so if we look at that then, and if it stays the same, if we do have that situation where it stays the same, then a value that stays the same, we have a derivative of equal to 0. So we can take a look at it using a calculus approach as well. Likewise with the sequence minus 1 over n, we can take a look at this algebraically. This is minus 1. This is minus 1/2. This is minus 1/3. So these are non-decreasing. And if we take a look at that using calculus, that function looks something like this. And so if we took a look at the derivatives here for a non-decreasing function, those derivatives are all bigger than 0, or in the case where we have the value staying the same, the derivative would be equal to 0. And so we can take a look at this just by patterns in terms of monotonic, or we can take a look at this by finding the derivative and making a determination based on the value of the derivative. And so if we look at this example here, we're going to talk about finding the limit first of all. So let's find the limit as n approaches infinity. I'll write it in sequence notation. And so we have 3n over n plus 2. I'm going to use L'Hopital's because right now that's infinity over infinity. That's indeterminate. So I'm going to use L'Hopital's to see if I can get this into a determinate form. So the derivative of 3n is 3. The derivative of n minus 2 is 1. That works out real nice. The limit is 3. So this sequence goes to the value 3. And if I want to prove it's monotonic, I personally like the idea of using the derivative. So I'm going to find the derivative of this function. So this function is 3x over x plus 2. That gets to be a bit nasty derivative. Using the quotient rule, though, we take the derivative of the top times the bottom. So we're looking at taking the derivative of this. So derivative of the top, that's 3, times the bottom, x plus 2, minus the derivative of the bottom, which is 1, times the top, which is 3x, all over the bottom squared, x plus 2 squared. And so if we simplify that, we're going to get 3x plus 6 minus 3x all over x plus 2 quantity squared. And so we're looking at 6 over x plus 2 quantity squared. And that's the value of the derivative. So if we look at that, 6 is always greater than or equal to 0. And x is also the term number, right? And we talked about the domain being positive integers. So x plus 2 is always greater than or equal to 0. So we know that the derivative is always going to be greater than or equal to 0. And that being the case, this has to be a non-decreasing function. And so if we would graph this then, function. There we go. If we would graph this function, then we'd have 3x divided by x plus 2. If you look at that graph, we're not going to pay attention to the negative domain here. We're just going to be able to pay attention to the positive domain. So I'm going to go ahead and set that at 0. And we'll set this at -2 and maybe 5. And so we're just taking a look at that positive domain. And we see that that function is always increasing. In other words, it's non-decreasing. So if we look at the derivative there, we always have that positive derivative along the values of the sequence. And we, 1, 2, 3, we look at the fact that there's that upper bound in 3 that the value of that function is trending towards. Now that we have an idea of what monotonic means, we can actually come back to this previous page. I'm going to grab that graph that we just threw on the page from the graphing calculator. There we go. And I'm going to copy that and paste it, because we have to talk about the idea of being bounded. And a bound basically is exactly what you know, have talked about in the past. A bound it has an upper bound or a lower bound, or sometimes both. And so when we talk about this, we know this is non-decreasing, it's monotonic. We talk about a bound here, and a bound is that asymptotic behavior. So for this previous example, this was the 3n, this was the 3n over x plus, or n plus 2. Which had a limit of 3, that we would call an upper bound. That's the maximum value we're going to see in the list of the sequence. So a sequence is bounded above if there's a real number m such that all of the terms are littler than that value. So for this, all of these terms are littler than 3. So there's an upper bound here of 3. Likewise, it can be bounded below if we find that minimal term, that value for which all the terms that value is a minimum term. And so, you know, the upper bound, all the values exist below the bound. For a below or a lower bound, all those values exist above it. And then it can be bounded both above and below as well. It can have both an upper and a lower bound.